So lesson 5.2 is linear models and functions. I would pause the video and write down these notes. So linear model is something of the form f of x equals mx plus c, where m and c are constants. Specifically, m is the slope of your line or your gradient, and c is your y-intercept. So the graph of a linear model is a line. We call these parameters because m and c are constant, but for every situation they change. So they're not variables, but they do change depending on the situation. The variables are your unknowns, so usually x and y, or whatever variables you're using to represent it in a given situation. Rate of change is the same thing as gradient, so that's your m value. It's the increase or decrease in the independent or the dependent variable for every unit of increase in your independent variable. So every time your x value goes up by 1, what's happening to your y values? It's increasing if it has a positive rate of change, so as your independent variable gets bigger, so does your dependent variable. It's decreasing if it has a negative rate of change, so as your independent variable gets bigger, your dependent variable gets smaller. So here's an example where a chemistry experiment, a liquid is heated and its temperature is observed. This graph shows the temperature of the liquid in capital T degrees Celsius, lowercase t minutes after the experiment starts, up until the end of the experiment. So use that graph to answer questions A through D. Go ahead and pause the video and do that. So part A says state the length of the experiment. So if we look at the x-axis here, it goes from 0 minutes to 10 minutes. So the length of the experiment was 10 minutes. Part B says estimate the initial temperature. So that would be your y-intercept. So I looked over here at time 0. It looks like it's at about 20 degrees Celsius. Part C says to estimate the rate of change of the temperature. So it ended at 320 degrees and it started at 20 degrees, and it took 10 minutes to do that. So I set up a little slope formula here. So it changed 300 degrees over 10 minutes, so that would be 30 degrees Celsius per minute. So suggest a formula, so I wrote a little function here. The rate of change was 30 times t because per minute, and then plus the initial temperature of 20 degrees. A different chemistry experiment lasts 8 minutes. A liquid is heated and its temperature rises at a constant rate, so that means it's linear. The initial temperature of the liquid is 40 degrees Celsius, and the final temperature is also 320 degrees. So now find the formula for this new chemistry experiment. Go ahead and pause the video and do part E. So I found my rate of change again. So it started at 40 degrees and ended at 320 degrees. So it went up by 280 degrees, and it took 8 minutes to do that. So that means it went up by 35 degrees Celsius per minute. And then our initial value, or our y-intercept, was 40. So I have t of t is equal to 35t plus 40. So here's another example. A water tank drains at a constant rate. Whenever you see constant rate, you should be automatically thinking linear. It contains 930 liters of water 3.5 minutes after it started to drain. It takes 50 total minutes for the tank to empty from the beginning. Let W be the amount of water in the tank in liters, t minutes after it started to drain. So for part A, we want to find a model that represents the water at any point. Part B says to write down the amount of water in the tank when it starts to drain, so the initial value. And then part C, use your model to find the amount of water in the tank after 30 minutes of draining. So go ahead and pause the video and try this example. So the first thing that I did was I found our rate of change. So I used the point 3.5 comma 930 and 50 comma 0. So in the y's, I did 0 minus 930, and in the x's, I did 50 minus 3.5. So at 50 minutes, it had 0 liters. At 3.5 minutes, it had 930 liters. So it went down 930 liters in 46.5 minutes, or it decreased 20 liters per minute. So the very first thing that I did when I wrote my model was I wrote it in point-slope form. So if you remember back from chapter 4, we talked about point-slope form. Y minus your y coordinate is equal to m times x minus your x coordinate. I just moved this y coordinate over, and I used the xy coordinate 3.5 comma 930. So my original model was Wt is equal to negative 20 t minus 3.5 plus 930. And then I used that to help me find my initial value. So I plugged in time to be 0, and I found that the initial amount of water in the tank was 990 liters. So then you could rewrite your model as -20 plus 990 if you want it in point slope intercept form. So then using your model however you wrote your model, we plug in 30 for time. So if you plug in 30 for time, after 30 minutes of draining, there would be 390 liters left in the tank. Some more notes about linear functions and models. One of them is directly proportional. So if a model is directly proportional, that means that one variable is a constant multiple of the other. We also call this a direct variation, which is anything that is of this form. So a linear model of the form y equals mx, which means your y-intercept is always 0 because you always just multiply one variable by something to get the other variable. The gradient, we call it the constant of proportionality, and because there's no y-intercept, or the y-intercept is 0, for any point x, y on the graph, the gradient or the constant of proportionality is always just the y-coordinate divided by the x-coordinate. So in this example we're going to look at, we're going to be converting between pounds and kilograms. So you're going to use this graph here to help you, for part A, convert 20 pounds into kilograms. We want to, part B, find the number of kilograms equivalent to 1 pound, which then we want to rewrite that as the gradient of the line. And then we want to find the model k of x, where k of x is the number of kilograms, and x is the number of pounds, and then use your model to convert. So go ahead and pause the video and try that. So I looked at the graph for part A, and I converted 20 pounds, so I went to 20 pounds on the x, and I found that it was equivalent to 9 kilograms. So then for part B, find the number of kilograms equivalent to 1 pound. So if 9 kilograms is equivalent to 20 pounds, I did 9 divided by 20. 1 pound is equivalent to 0.45 kilograms. Hence, write the gradient, it's just this because it's y divided by x, so 0.45 kilograms per pound. Find the model. Since it's a direct variation, it's just k of x is equal to 0.45x. Whatever your pounds are, you multiply by 0.45, and that's your kilograms. So then for part EI, you plug in 17 for x, and you end up with 17 pounds is 7.65 kilograms. And double I, we want 25 kilograms, so we're going to plug that in for k of x and solve for x. So divide both sides by 0.45, and 25 kilograms is a little over 55.6, 55.5 pounds. So whenever you have something that's a direct variation, you just divide the y-coordinate by the x-coordinate because your y-intercept is always 0. Simultaneous equations are when you're trying to solve a solution of a system of equations. Basically, you're trying to find where they intersect, what solution satisfies both or all of the equations. There's 4 main methods. The first one is substitution method. Solve one of the equations for one variable, plug that into the other equation, substitute, solve for your remaining variable, plug that in to find whichever you have variable left over. Elimination method, multiply one or both equations by something so that one of your variables will cancel out when you add them together. Add them together, cancel out that variable, solve for your remaining variable, plug that back in to find your other answer. Graphing method, graph the 2 equations, find where they intersect. That's not super easy to do by hand, but we can do it pretty easily on the graphing calculator. Or the other method on the graphing calculator is the Simultaneous app. So sketch the equations f of x equals 2x plus 3.5 and g of x equals 0.5x plus 7. You can use your graphing calculator, and then use a method to find the intersection point. So I sketched a graph right here. The red line is f of x equals 2x plus 3.5. The blue line is g of x equals 0.5x plus 7. So you can see this intersection point, but it's not in a very nice spot. I can't just read off the answer very easily. So I solved this using substitution method because they were both already solved for y. So I just set them equal to each other and solved for x, got x to be 2.33, and I plugged that into f of x and got y to be 8.17. So the intersection point is 2.33, 8.17. This also would have been pretty easy to solve with the graphing calculator method with the intersection function. The next part is about inverse functions. I would pause the video and write down these notes. So if you have a one-to-one function f that maps a, your inputs, onto set b, your outputs, then it will have an inverse function, which we label as f inverse, that maps b, the original set of outputs, onto a. So basically it undoes it. So when originally you're going from a to b, your inverse function goes backwards from b to a. If f of x is equal to y, so those are your y coordinates, then this notation for f inverse, it switches your x's and y's. So f inverse of y is now your x. It undoes it. Thinking of it like as a squared, x squared versus the square root. They undo each other. Your independent and your dependent variable sets are switched, and they undo each other. So this is the notation. This -1 power doesn't actually mean a -1 power. It doesn't mean 1 over f of x. It's just strictly the notation. So whenever you see this, it means the notation for inverse functions. A function and its inverse are reflexive across the identity line y equals x. So if you look at a graph, you can find inverses or graph inverses by reflecting across the line y equals x. The domain of the inverse function is the range of the original function, and vice versa. The range of the inverse function was the domain of the original function. So the domains and the ranges of inverse functions are switched. If you want to find an inverse function, the first thing that you do is you take your original function, you switch x and y, then you solve for y, and label your new function as f inverse of x. So here's an example where we have a graph of f, and we want to use the graph to find f of 2 and f inverse of 9. So go ahead and do part AI first. So go ahead and pause the video and find f of 2. So if we look at the graph, we find this is saying when x is equal to 2, y is equal to what? So we go over here, when x is equal to 2, y is equal to 5, or f of 2 is equal to 5. The next part says f inverse of 9. So basically we want to undo this. The way that I like to think of it is, okay, f inverse of 9, that is now equal to our x value, because inverses were our original x's. So this is the same thing as saying f of x, the original function, is equal to 9. This, if it's inside your inverse, was your original y value, and now we're solving for x. So when y equals 9, what does x equal? So go ahead and pause the video and find a double I, and then also use that same idea to solve the equation f inverse of a is equal to 1. So a double I is saying f inverse of 9, which is the same thing as saying what is your x value when y is equal to 9. So I went over to my graph, I found y equals 9, and found my x to be 4. So on these questions, I find it easy to kind of undo them and see what they're asking. So same thing on this one, f inverse of a is equal to x, 1. Well, if it's an inverse, your output is your original x value. So if you switch this, this is really saying f of 1 is equal to a. So if I go over here and I find 1, then my y value at x equals 1 is 3. So this is asking what is your y value when x is equal to 1. The last example says find the inverse of the 1-to-1 function f of x is equal to 2x plus 5. So go ahead and look at the steps from the last slide and find the inverse function for this function. So I switched x and y, f of x is the same thing as y, so now I have x is equal to 2y plus 5, so I just switched my x and y in my original function, and then I solved for y, so I subtracted 5 from both sides, that's going to undo the plus 5, and I divided both sides by 2, that's going to undo the multiply by 2, and so my new function, once I switch and relabel this as f inverse of x, is x minus 5 over 2. So you're undoing in the opposite order. Originally you multiplied by 2 and then added 5, so now in the inverse you're going to subtract 5 and divide by 2. So this has been linear models and inverse functions.